So, okay, I think I managed to do it. I'm not sure if it's fine.
It's
okay.
working.
Okay. So I'm sorry for the delay. Okay, so I will be speaking about the Floquet spectrum of 2D Dirac materials under a periodic drive, the monodromy, through the monodromy matrix approach. And I'm from the Universidad Autónoma Metropolitana from Mexico City. And so first of all, I would like to thank the organizers for organizing this event. It's quite nice to have the possibility to attend online events since it's now at the moment it's impossible to go anywhere. So I thank them very much for giving the opportunity of this community to get together and share our results. And well, for inviting me too, I'm very thankful with the organizers. So my collaborators are Victor Ibarra from Ensenada, and Juan Carlos Santana also from Ensenada, and Gerardo Naumis from the Physics Institute in UNAM. And we have been working together in some aspects of graphene, so 2D materials, especially graphene and borophene, and under the influence of an electromagnetic field in normal incidence. And okay, so the outline of my talk, I will give a very brief introduction. I will explain later on how you can use the monodromy matrix approach to calculate the quasi-energy spectrum of any system. In particular, I will show how to do it for 2D Dirac materials. Then I will speak about a Rabi formula and the transition probability between the valence and the conduction band in graphene and borophene. And later on, I will give you some of the results that we have been able to obtain through the low energy Hamiltonian. And at the end, I will show some preliminary results that we have on the tight binding approximation with the same technique, with the monodromy matrix technique, and then I will conclude. So basically, 2D Dirac materials have outstanding properties. They have outstanding electronical and mechanical properties. For example, they allow to explore new quantum phases. For example, in the photovoltaic Hall effect and the light-induced anomalous Hall effect. And they also offer next-generation electronic devices as terahertz generators, plasmonic devices, polarization sensitive broadband photodetectors, broadband optical modulators, infrared photodetectors, and solar cells, and a bunch of other electronic applications. And so what I'm interested in this talk is that in graphene, we have the electronic dressing of electrons, renormalize the properties, the electronic properties, or renormalize the electronic parameters. And the idea would be to use the renormalization of these electronic parameters to design the properties, to design new properties that could be used in future devices. So I will also be speaking about borofin, which is similar to graphene, but is anisotropic and it's also tilted. So, for example, in the case of borofin, in the case of graphene, you have the two Dirac cones, which have this very symmetrical structure. But when you analyze borofin, then you find that the spectrum of borofin is not, it's tilted and it's also anisotropic. So the cross section while the cross section of this spectrum are circles, the cross section in borofin are tilted, and anisotropic. Okay, so our ultimate objective in this work is to find the quantized Berry phase. Okay, so in graphene, the quantized Berry phase, which is equal to pi, is the accumulated phase due to massless relativistic electrons along one cyclotron orbit. And in this case, this is the evidence, this is evidenced by the anomalous quantum Hall effect. But it has been shown lately that the Berry phase can also be observed through the insertion of hydrogen impurities in graphene through the in the absence of magnetic field. Okay, but so as I was saying, our ultimate goal in this work is to calculate the Berry phase of graphene under strong normally incident electromagnetic field. However, I will not address the Berry phase on this talk because because my results are not conclusive yet. So, but that's our ultimate goal. And maybe on Thursday, Gerardo will make some comment on this, but I will only talk about the preliminaries of these calculations. Okay, so I will be studying the effect of graphene and borofin strongly interacting with a normally incident electromagnetic field, which is circularly or linearly polarized. And I will center the discussion on the quasi-energy spectrum and the valence to conduction band transition probability. If you're interested in this topic, then you can check any of these two papers, and most of the results that I will be speaking of today are summarized in these two papers. Okay, so in this first part of the talk, I will start with the low energy Hamiltonian in the K valley, which is given by this expression. These are the Pauli matrices. And this is just the identity matrix, the 2x2 identity matrix. So this Hamiltonian is for borofin. And so in the case of graphene, you don't have this term. This term is 0. And you only have these two terms in the low energy Hamiltonian. Here you can find the velocities for borofin. And as I was saying, in the case of graphene, you only have Vx and Vy, and both are equal to 1 the Fermi velocity, okay? 1 time the Fermi velocity. So under an electromagnetic field, the only thing you have to do is insert the components of the vector potential next to the momentum operators. And in the case of normal incidence, the vector potential is given in terms of the electric field by this expression. And this phase here helps me to switch from linear to circularly polarized light. Okay, I can go gradually from linear to circularly polarized light just by switching this phase from 0 to pi divided by 2. And so, I mean, this is a very convenient way to study the interaction of the Hamiltonian, the interaction of graphene electrons with a source of light. Okay, so, so the problem is that when you have a time-dependent Hamiltonian, then the energy eigenstates have no meaning at all because you have time dependence in the Hamiltonian. So you're forced to look at the quasi-energy spectrum, which is something that I will explain in the next slides. So the Schrödinger equation for the evolution operator, which is this U here, is this equation here. And the time-dependent Hamiltonian has all these terms where I just have inserted the explicit form of the vector potential into the previous Hamiltonian. And okay, so as you can see, this Hamiltonian is time-dependent, so there's no way I can calculate energy eigenvalues from this Hamiltonian. However, I can calculate the quasi-energy, and that can help me to compare with the case where the Hamiltonian is time independent. That is when the light incident on the sample is absent. And so what we use to calculate the quasi-energy spectrum is use the Floquet theorem. The Floquet theorem says that if you have a periodical Hamiltonian with period t, then the evolution operator can be expressed as this. So you have Wt, which turns out to be a periodical operator or a periodical matrix, and you have this term which is very similar to the evolution operator, but it only works for integer periods t. So this term is the Monotromy Matrix, and He is the effective Hamiltonian, this He here. Okay, so the effective Hamiltonian only works each period of t, and so in some sense you retrieve the evolution operator that you have for time independent Hamiltonians. So this term, which is the Monotromy matrix, is obtained by numerically calculating the evolution operator up to just one period t. That is very convenient because you don't need to evolve for long periods of time. You just need to go to one period, and then you basically know everything about the time evolution of the system. And of course, for the evolution operator, you can set the initial condition for the evolution operator to be the identity at the beginning of the experiment or at the beginning of the evolution. And therefore, for one period, the evolution operator is given by this form, which, as I said before, resembles the traditional form of the evolution operator for constant Hamiltonians. So the instead of calculating the energy from the Hamiltonian, in this case, you calculate the energy from the effective Hamiltonian. But I meant that you calculate the quasi-energy from the effective Hamiltonian. Okay, so the problem with this picture is that the quasi-energy of the Hamiltonian is limited to one Floquet zone, which starts in minus pi and ends in pi. So if the energy, so in one Floquet zone, we will have repetitions of the energy, and this sometimes can be a little bit confusing, but it's the best thing we have to compare with the energy. Okay, and so this is how. So this is basically how I calculate the quasi-energy. This is the method to calculate the quasi-energy. But so let me move on to the technique I will use to obtain the probability transition between conduction and valence band under the different illumination situations. Okay, so first, to establish how these transitions occur, I need a transition time. So this, I don't it's not that easy to find a transition time. So for this reason, we calculated a Rabi-like formula, which has, I mean, this is the probability, the transition probability between the conduction and the valence band. And as you can see, this probability has a very similar shape to the transition probability given by the classical Rabi-like, the classical Rabi formula for two-level systems. However, these two expressions are quite different. I mean, for example, the transition time, this is this omega term is related to the transition time, and as you can see, is similar to the one found in the Rabi formula, but not quite. And the detuning parameter looks almost exactly the same. However, it has an integer here. So that gives the indication that we will have multi-photon processes in the transition probabilities. And here, this is the free electron spectrum. This here is the free electron spectrum, which is the traditional free electron spectrum for graphene. And as I was saying 2 seconds ago, a full transition occurs when the detuning parameter equals to 0. But as you can see here, since this Q is an integer number, then for Q equal to 1, we will have, I mean, we will have one photon processes, and we will also have multi-photon transitions. Okay.
Well, I'm sorry. The question, in the time that you're using U of t, this is an arbitrary time, or has to be a multiple of the time of the capital time you introduced before?
No, this is the, I mean, I think you mean this time here.
Yes.
Okay. No, it's just, it can be any time. It doesn't have to be the period capital T.
But didn't you say that you calculate, I mean, you calculate the energies, no, the quasi-energies, and this, yes, you use, you have to use the period capital T, and this with this energy you calculate the evolution operator. So I'm confused about that.
No. I just used, I mean, this expression. Yes. Well, I'm glad that you brought this up because, okay, so
here you're missing a capital T anyway, no? In the formula that you just remarked.
No, not necessarily. Not necessarily. Yes.
No,
I
but
mean,
in the other transparency, please, there. U of
yes,
capital
you're right.
T cannot be function of small t.
Yes,
Yeah,
you're right.
okay. So
you're
this
right.
is capital T.
This is in here you have a capital T.
Yeah, and you calculate the evolution operator for capital T.
Exactly.
Just for capital T.
Oh, I didn't understand your last remark, but okay, this should be capital T. You're right, there's a mistake there. But in this formula, this time here not necessarily is capital T.
So you know U of T for every T.
Yes.
Well, I had the impression that it was just for capital T.
No, because I mean, for most of my calculations, I used the complete evolution operator because I calculate it numerically. So I mean, I could use just the effective Hamiltonian, but in all my calculations, I use the whole evolution operator.
Okay. So the calculated in another way.
The quasi-energies are calculated only with the effective Hamiltonian, but all the calculations that you will see in a minute are calculated with the whole evolution operator.
Okay.
So there's no approximation. Just this formula uses the rotating wave approximation, but this formula is only used to obtain a transition time. That's the use of this formula.
Okay. Thank you very much.
No, in fact, it was good that you asked that question because I had a mistake in the previous. Okay, so from this omega here, this omega here, okay, so from this omega here, I can calculate the transition time between the conduction and the valence band. And as you can see, even though it looks similar to what you would obtain in the classical Rabi formula, this gamma term here, which enters the transition time here, it's very complicated. And I mean, I don't want you to look at the detail of this expression. I would like to raise your attention to this term here. So as you can see, this is a Bessel function, and the only Bessel function which is equal to 1 when the argument is equal to 0 is the 0-order Bessel function. So that corresponds to 1-photon processes. And here you have multi-photon processes. So since the argument of the Bessel function is proportional to the intensity of the radiation that you apply on the graphene layer, then you see that as the intensity of the radiation increases, more and more photons are involved in the transitions from the valence to the conduction band. So that's the meaning of this result. So, okay, so that's the transition time. And now just I have one remark on the Rabi formula. I would like to say that in contrast to with the classical treatment of Rabi oscillations, where only one oscillating mode is present, here the Hamiltonian is composed of an infinite number of Fourier modes. And this is our first evidence as to why multiphotons modes are generated in Dirac materials, while in standard Rabi systems, only the single photon one is present. Okay, so we have multi-photon processes. Okay, so let me show you the results. Okay, so first let's see what happens with the quasi-energy spectrum. So when I turn off the incident light, that is that the components of the electric field are zero, then I recover the very familiar Dirac cones that you can see here. Of course, so here in inset A, you can see detail of the Dirac point. And in this section, you have the whole quasi-energy spectrum. So as you can see, so you have the cone, and then you have repetitions of the cone due to the finite Floquet band that we are observing here. So if you want to recover the Dirac cone, what you have to do is translate the different sections of the cone, and you would recover the cone form of the spectrum of the typical of graphene. Okay, so in the bottom side of this figure, you have the two different cross sections of the spectrum. So one is along the kx component of the momentum, and the other one is along the ky component of the momentum. And as you can see, in both cases, I mean, for example, if you follow this line here, if you follow this line, you will see that you have recovered the cone, the first cone, and here you have the Dirac point. And the rest of the triangles and the squares that you see next to this point are repetitions due to the finite Floquet band that we are observing. Okay, so this is with no electromagnetic field. Okay, so we basically recover the Dirac cone. Okay, now if we introduced linearly polarized light, we see that inside of close to the Dirac point, in the vicinity of the Dirac point, there's a strange form of the spectrum that looks like an American football. Okay, so, and as the size of this circle is given by the intensity of the electric field of the radiation. And so as E becomes larger, this circle becomes larger. And what's amazing about this result is that the transition between the free electron spectrum and the intense light and the intense intensity, and the very intense electric field region is very abrupt. It finishes very abruptly. There's no transition. There's no smooth transition between one region of the spectrum and the other. So in the bottom side of this figure, you can see again two cross sections of the spectrum. And as you can see, along the ky direction, the spectrum is completely distorted, but along the kx direction of the spectrum, the spectrum is untouched. In fact, if I had only shown you the kx cross section of the spectrum, you wouldn't be able to tell that there's a difference in this case with the radiation. So, and another thing that's important is that the quasi-energy spectrum is distorted along the perpendicular direction of light polarization. So in this case, light is polarized in the X direction, and the distortion is observed in the Y direction of the spectrum. Okay, so this is linear polarization. So the another thing that's important to realize here is that the Dirac point remains in the same place due to the fact that light is linearly polarized. But something interesting happens, and is that we have these new Dirac points, which are, I mean, I like to call them Dirac points, but I'm not sure they have the same properties as Dirac points. One way to check that would be to calculate the Berry phase of these Dirac points. But as you can see, you have new Dirac points that are formed in the region of strong electric field, which is inside this circle. Okay, so now I change, so I move to circularly polarized light, and the result I obtain is completely different. As you can see, in both cross sections of the spectrum, I observe the formation of a gap, and the Dirac point completely disappears. So this is, well, this is not strange, but again, the deformation of the quasi-energy spectrum is circumscribed to this region, which is given by the intensity of the electric field. Okay, so but as you can see here, you can use the polarization of light to open up a gap inside the quasi-energy spectrum. Okay, so let's see what connection there is between the transition times and the quasi-energy spectrum. Okay, so in the weak field regime, as I told you before, there's only one photon processes, and so basically we only, I mean, this is the probability, the transition probability, and in each k point of the spectrum, I have chosen to a transition time which is equal to the one you saw a few slides ago, that it's deduced from the Rabi formula. So that guarantees that I will have a full transition between the valence and the conduction band. And so as you can see, in the weak field regime, we have the expected result. The transitions only occur when the detuning parameter is equal to 0, and so you get full transitions. However, in the electric, when the electric field of the radiation is linearly polarized, you have these directional effects on the transition probability. So there are regions where there are directions in which the transition probability is 0, and this is very interesting, and we have recently found that this is connected to the value of the Berry phase in these cases, but I will not be discussing that because I'm not so confident on those results. Okay, so this is under linearly polarized light, and when we turn to circularly polarized light, we basically obtained a very symmetric transition probability profile, which is again given by when the detuning parameter is equal to 0 for one photon processes. Okay, so if we move to the strong field energy regime, strange things begin to happen. So as you can see, here the transition probabilities are not circumscribed to the strong field regime. They are all over the place for linearly polarized light and for circularly polarized light. But in the case of circularly polarized light, you can see multi-photon processes more clearly than in linearly polarized light. So this circle here gives you the one photon transition processes. And as you can see, there are other circles around the one photon process, which correspond to multi-photon processes that are given by different by multi-photon processes. Okay, so another way so what would be the way to measure these transitions, and or what would be the what physical quantity can we use to have evidence on these multi-photon processes? Well, the photocurrents are a good example because they depend strongly on the transition probabilities. So here we calculated the density matrix of the time-dependent density matrix. And here, for example, the time here is completely arbitrary. I don't need to go to one period, for example. This is completely arbitrary. And I'm doing these calculations at low temperature. And as you can see in the weak field regime, the only so here we have the Fourier transform of the different Fourier components of the current. And as you can see, in the weak field regime, the dominant one is the one that corresponds to 1 omega. I mean, that's the frequency of the drive. That's the fundamental frequency of the drive. And as you increase the intensity of the electric field, multi-photon processes are activated, and we have more components of the current. We have different harmonics of the current that can be appear. In fact, the 2 omega component is very strong in the case of linearly polarized light. And the same thing happens with circularly polarized light. You have different harmonics in the current, which are participating in this phenomenon. Okay, so let me rapidly move to what we're doing. This is our most recent, these are our most recent results, which are done on the tight binding approximation. The nice thing about the tight binding approximation is that it's very easy to put boundaries on the system. And that's why we are very attracted to this model. So the first thing we wanted to check is that the tight binding approximation gives us similar results. For example, in the quasi-energy spectrum, we would like to see if the tight binding approximation gives us this football that we find on the strong field regime of the spectrum. So this is the tight binding, this is the standard tight binding Hamiltonian, where each one of these states is one of these states on, I mean, is the occupation on the different points of the graphene lattice. And these are the, well, these are the lattice vectors. Okay, so there's nothing strange about that Hamiltonian. And we can we can then obtain the tight binding Hamiltonian in the momentum space. This is all very standard. And then we calculate the spectrum. And here you can see the two valleys, okay, of the spectrum. I mean, this is just to develop a common language for the next slide. So this is all very well known. And in this picture here, you can observe the two valleys of graphene. Okay. So, and I'm interested in what happens along this orange line, because in the K space, this gives me the direction of the zigzag. If I cut a graphene strip, a zigzag graphene strip, then this would be the line I would be looking at in the momentum space. Okay, so let's see what happens under linear polarization. So if the electric field of the radiation is 0, then we just see in the quasi-energy spectrum the same structure that we saw on the energy of the time-independent Hamiltonian. And as we switch the electric field or the radiation in linearly polarized radiation, then we observe the formation of the football inside each of the two valleys of graphene. I mean, it doesn't, the electric field is oriented in this direction. So that's why the football is tilted inside the two valleys, okay? So as you can see, the football is pointing in opposite directions depending on which valley we are dealing with. Okay, so here you have a detail of the football, and you can see that it resembles the one that we obtained for the low energy Hamiltonian, and that's interesting. Okay, so now what we would like to understand is what happens if we cut a strip of graphene, a zigzag strip of graphene. We haven't tested armchair yet, but it's in our future plans. And what we want to see is what happens to the quasi-energy spectrum in this case. Okay, so here, I mean, this picture is the one that you just saw a few seconds ago. This is a graphene with an infinite number of carbon atoms. And in this case, what we are doing is we are collapsing all the states along the K2 direction, which is perpendicular to K1 in this direction. And what we see is this energy spectrum. And here you can see these two valleys. I mean, you're seeing this valley and this valley. You can see these two valleys, and you can see the two Dirac points here. Okay, this is pretty standard and normal. This is a pretty standard and normal calculation. Okay, so, and what we're doing here is we cut the strip to 20 carbon atoms, and what you see is pretty much the same, but you have these extra levels here, and you can identify the values that you used to have when you have an infinite number of carbon atoms. And in this picture, I have superimposed the two cases. Okay, now the problem is that at this point, I'm not able to, I will have to move on to the conclusions because I cannot show you what happens in this picture with, I cannot show you the football. I cannot show you the effect of the football in this spectrum, because since what I'm calculating is the quasi-energy, I observe a lot of repetitions in the different Floquet zones. So it's very difficult to observe what happens with the electric field. So what we are doing now is trying to identify a suitable regime in which the football is observed for a zigzag strip of graphene or borophene, it doesn't matter. And we're trying to see what are the effects on the boundaries of the system. But this, I'm not really sure right now what we have, so I prefer not to show you those results right now. Okay, so I would like to conclude. So we have studied the influence of strong electromagnetic field on the charge carriers of borophyrin and graphene. We have calculated the quasi-energy spectrum, the transition time, and the induced photocurrents. And the obtained Rabi formula reveals the presence of multi-photon generated high harmonics. So this could be used to generate high harmonics in graphene. I mean, this idea could be used to generate high harmonics using very intense electromagnetic fields on graphene. And another interesting thing is that multi-photon processes induce transitions well away from the fundamental transition. That means that not only the detuning parameter can become zero, not only on the one photon transition, but it can become different to zero. It can become zero. It can vanish for multi-photon processes too. So you have multi-photon transitions. And I couldn't write the last two remarks, but what we can say is that at least the deformation of the quasi-energy spectrum that we observe for linear polarization in the low energy Hamiltonian is reproduced in the tight binding Hamiltonian. And in the future, we would like to calculate also transition probabilities and basically repeat the same calculations that we did on the low energy Hamiltonian, but for the tight binding Hamiltonian. So that's all. So thanks for your attention.
Okay, thank you for the interesting talk, Alejandro. Let's move on to the questions. Are there any questions from the audience?
I have a question.
Yes, go ahead.
Yeah. So this last states that were centered around zero quasi-energy, are they special in some way? Are they, let's say, topological or something in that style?
That's an excellent question. That's an excellent question. But the thing is that I have no answer. The answer is I don't know. That is a question we are trying to answer. It's really difficult to calculate, for example, the very phase around this point. Let me show you why. But as I'm saying, for me, I'm not sure about anything I'm saying here. So usually when you calculate the very phase around the Dirac point, you have the explicit form of the wave function of graphene. And so it's very easy to do the integral of the very phase as you would calculate it for the case of a quasi-static time-dependent potential. So you go around the Dirac point and you obtain pi. That everybody knows that. It's very easy to calculate. The problem is that when you have time-dependent Hamiltonians, and in this case, inside this zone, inside the football, you are outside the football, you have quasi-static conditions, so you could calculate the very phase, no problem in this region, with no problems at all, because you would basically recover the free electron picture that you had at the beginning. However, when you are inside the football, you are not in a quasi-static, you are far away from quasi-static conditions. So it's very difficult to calculate the very phase. And we have calculated it, but we don't have definitive results. But it would be very interesting to know, for example, what is the very phase around these peaks here. But it's we still don't have any results on that. Well, we have some results, but they are not definitive, and they are not conclusive, I think.
But so the appearance of these states depends on a strong coupling of a strong intensity of the light?
Yes, yes,
okay.
Yes. In fact, inside this circle here, the intensity of the light, I mean the energy due to light, the photon energy is stronger than the energy of the electrons. So that's why the quasi-energy spectrum is completely distorted in close to the Dirac point.
Okay, thank you, Alejandro. Are there any other questions? Or meanwhile, I have one question. In the slide 25.
25.
Yeah, it's almost at the end. Yeah. When you put the spectrums
yes,
superimposed, yeah, I can say that there's a gap. Well, in the right figure, there's a gap in one cone or one valley, and in the other cone, there's no gap. Is there any reason to that? Or
I mean, okay, why there's a gap here? And well, the thing is that these are the valleys, but these are not valleys, because what you're seeing, the first, so this is, okay, so this point here corresponds to this point here. And this point here corresponds to this point here. So this point here corresponds to this point here. So you're not really in one of the valleys, so it's another thing. So that's not a gap. But one thing I have been seeing lately is that when I turn the electric field, I think it was the case of linearly polarized light. One of the gaps, you have a gap in one of the valleys, but you don't have a gap in the other valley. And that's quite strange. I don't understand why that happens. So, but that's why I didn't show those slides, because I'm not sure if it's some error in my calculation or I don't understand it yet.
Okay. Well, thank you.
No, thank you.
Another question from the audience?
Yeah, just a very general question. I mean, is there any approximation for, I mean, any, not numerical, but analytical approximation for the calculation of the evolution operator in the simple case that you mentioned, where you have, not in the general case, but when you have this incident electromagnetic field, which are rather simple compared to a general situation. What I mean, is there any analytical approximation of the evolution operator, or you just have to calculate everything numerically?
I have to calculate everything numerically. I mean, for example, in the case of the low energy approximation, my only approximation is that I use the low energy Hamiltonian. That is the only approximation. And I also suppose that I'm under normal incidence, because if you have oblique incidence, then things become really difficult to calculate.
I guess, yes.
Yes, but that is my only approximation. And in the case of the tight binding, in the tight binding Hamiltonian, my only approximation is that I use the tight binding Hamiltonian. And aside from that, there's no other approximation. I have to solve the equations numerically.
Numerical, okay.
We have tried other approaches like using Lie algebras, because the elements of the tight binding Hamiltonian in momentum space and the elements of the low energy Hamiltonian in momentum space both belong to finite dimensional Lie algebras. So you can find a closed set of differential equations, but these equations are so complicated that it's useless to try to solve them in any other way. They cannot be solved analytically except for some special cases that probably Gerardo will discuss next Thursday. And so it's better to do it numerically.
Okay. Thank you.
No.
Okay, well, another question or comment? Well, just for the last minutes, I think I can go for another question that is in the slide 19 where you put the photocurrent. Okay.
Yeah, okay. Well, I'm sorry, I'm struggling with Zoom again.
Okay.
But
well, my question it was that in that figures, in the photocurrent, you have two rows, and the first row corresponds to the
linearly polarized case.
Linearly polarized, and the other to the circular. The linear polarized over the direction that you choose in that axis for the momentum, it's along the linear polarization, right?
Yes. No, it's in the, I'm not sure. I'm sorry. I don't remember.
Because you
no, I'm calculating the magnitude of the current. So the magnitude of the current. So it's not any direction in particular. And the angle you see below, it's the direction of the angle in which the light is polarized. Okay. So as you can see, you have these variations on the intensity depending on the angle in which you polarize light.
Okay. Well, thank you. Well, I think we thank to Alejandro for the interesting talk. And